Hi everyone, we're going to get started in just a minute or two. Hello everyone. On behalf of the Environmental Finance Center Network, welcome to the fourth session in our Operator Certification webinar series on disinfection and solids handling. My name is Kristen Crew from the Syracuse University Environmental Finance Center. Before we begin, we're going to go over a few logistics and then we can get started. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar question dialog box anytime throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. After the webinar, you will receive a follow-up email that includes a link to the recording and other information that you may need. You can also download the slides from today in the Handouts tab in your GoToWebinar control panel. This webinar has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the webinar date. If you have questions or need assistance, please contact smallsystems@syr.edu. Now for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our Building Technical, Managerial, and Finance Capacity program. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I will be sharing shortly in the chat. And on that note, we can get started. I would like to introduce our presenter for today, AJ Barney. He's a research scientist with the Southwest Environmental Finance Center. All right, AJ.
All right. Okay, so I got the screen share. Oh, there it is. All right, can everyone see the screen?
Yep, it looks good.
Okay, thank you. All right, so as I said, my name is AJ. Hi everyone. I'm a research engineer with the Southwest Environmental Finance Center, and just a little bit about me. I am a civil engineer and a biologist, and I've worked in wastewater for about 10 years. I have a New Mexico wastewater level 4 operator certification, and I previously worked at the Albuquerque Water Authority as an operator and in compliance before joining the Southwest Environmental Finance Center last year. So if any of you guys were with us last week, this is just kind of a refresher on certification requirements, and I'd just like to kind of talk about that first before I start the presentation, which is kind of based around certification requirements. So operator certifications are typically overseen by state environmental programs. Some examples from the EPA Region 6 are the Texas Commission of Environmental Quality, the New Mexico Environmental Department, and the Oklahoma Department of Environmental Quality. I noticed last week that there was a few of you probably are under those jurisdictions. There's also an EPA operator certification, which is designed to have reciprocity with state levels and is utilized by such communities as tribes, and then ones that aren't regulated by their states. So each agency has their own level hierarchy, and this is based on the different criteria the certification may serve, such as complexity of the system, the population size the certification can cover, and years of experience required to operate the plant. There are a variety of resources that each of the states offer, such as need-to-know criteria for the exams, study guides, and then there's also the California State University Sacramento Wastewater Operations Manual, which is a lot of this material is derived from that the states have, and is kind of the go-to for operators and wastewater treatment plants. So it's important to become familiar with those resources provided by your state to kind of know what's on the exam. So this webinar, I like to state this webinar series is a great overview for many of the topics we cover, but we can't go into enough detail to really give people the information, such as design criteria and stuff like that, really needed to know and be successful on the exam. So I would recommend noting the processes that we cover and diving into the details on your own, such as flow rates, detention times, expected concentrations, stuff like that. We'll talk about a little bit of it, but we can't really cover all of it in the hour that we have. I usually recommend people use multiple hours over weeks and months to be really successful. So on that note, let's go ahead and start the presentation. So this presentation is going to cover disinfection and solids handling. For disinfection, we're going to be talking about chlorination and dechlorination, as well as ultraviolet or UV disinfection, and then ozone disinfection. And then for solids handling, we want to talk about dewatering and digestion. So first of all, what is disinfection? So disinfection is the destruction of all pathogenic microorganisms. And the goal of disinfection is to remove all disease-causing pathogens before effluent is discharged into receiving waters. This helps protect our public water supplies, irrigation water use, and then receiving waters for recreational uses, and also shellfish growing in the areas. Now, this is not the same as sterilization, which is the complete destruction of all microorganisms, which is considered impractical. The level of chemicals and the level of treatment that we required is just way too strenuous. And then at the end of the day, you usually can't complete sterilization as well. So here's just a quick overview of some of the disinfection processes that we're going to cover. There's chlorination, which typically uses chlorine gas, chlorine powder, or liquid chlorine solutions to disinfect wastewater, treated wastewater. And then you also have UV systems, which uses ultraviolet light to inactivate microorganisms, which stops them from reproducing. When microorganisms are able to reproduce is when they really become an issue and become pathogenic, because multiple ones are able to get in your system and spread and kind of edge out good bacteria or just other small particles that are required. And then also ozone, which uses ozone gas to disinfect. So first off, we're going to talk about chlorination. This is the most common form of disinfection. This is the one that's been the longest used and the most studied. It can be applied in a variety of ways. We talked about those three: liquid, powder, and gas form. Now, chlorine is a good disinfection because it's a strong oxidizing agent, which that means that it's pulling hydrogen molecules off of organisms and particles, and it's very reactive. So chlorine is readily available and cost effective compared to the other disinfection processes. Like I said, we've been using this for a long time, so we're very familiar with how to acquire it and how to apply it. And it has a long track record of efficient disinfection, and it can also remove odors. So first we're going to talk about chlorine gas. The first thing to know about chlorine gas is that it's extremely hazardous. The reason that it is such a good disinfection is because that oxidation properties make it very dangerous to handle and to be exposed to. So it's toxic. It can be fatal if inhaled. It starts to, deposit hydrochloric acid and, oxidize your body tissues. It's also corrosive. That's where that hydrochloric acid comes into effect, where it can also deteriorate infrastructure and components of your wastewater treatment processes and the equipment that you use. It forms that hydrochloric acid when it's exposed to moisture, and that is typically just moisture in the air. It is an irritant for your skin, eyes, and lungs. When you come into contact with chlorine gas, you can very quickly realize that that's affecting your system. Your eyes will burn, your skin may itch, you'll have trouble breathing, you'll be coughing, that kind of stuff, and that's at very low concentrations. Chlorine gas is also explosive. For that reason, it's typically protected when there is a danger of someone attacking or like terrorists, stuff like that. And these large tanks can typically, they can explode and cause very high affected areas, miles and downwind and stuff like that. So it is very dangerous to handle the tanks as well. And even a small tank that falls can explode and cause a an environmental hazard. So here are some of the physiological responses to chlorine gas. So at very low concentrations, between 0.1 and 0.3, you can start to smell it. It has a very distinct smell. I'm sure a lot of you guys have been in pools with a lot of chlorine, even to the point where it is having those side effects where it's burning and stuff like that. That's kind of that detectable odor. And then between 1 and 3 ppm, real quick, just if anyone's not familiar with what ppm is, that's parts per million. So that means 1 particle for every 1 million particles of air. So you can tell that's not a whole lot if you have 1 to 3. And ppm is also the same thing as milligrams per liter. So at 1 to 3 ppm, you can have mucous membrane irritation. That's when it's affecting your eyes, your breathing. At 30 ppm, that's when you can start to feel chest pain, shortness of breath, coughing, stuff like that. And 40 to 60 ppm, that's when you can have toxic pneumonitis and acute pulmonary. Those are breathing issues that can be, that aren't just short term. And then at 400 ppm, it can be fatal over a 30-minute span. And then 1,000 ppm, it can be fatal within minutes. So that's not even 1%. That's 0.1% of the air is chlorine is fatal within minutes. So that shows how really toxic this substance is, and to kind of be aware of safe handling that it requires. So now that we talked about like the safety of chlorine gas, I just want to touch on some of the operational stuff and the chlorine requirements. So chlorine, when it's added to water, you're going to want to understand the chlorine dosage, the chlorine demand, and the chlorine residual. The dosage is calculated by the amount of feed that's over the flow. I'm sorry, it's divided the amount of chlorine that's fed into the water over the flow. The chlorine demand is the amount of chlorine required to act with all reactive substances in the flow. And then the residual is the remaining chlorine in the water after the demand has been satisfied. So you have how much you're adding, how much is used, and then what's left over. And typically you want to measure the chlorine residual, and your permit's going to have a requirement for that. So here's just a quick calculation of that. So it shows that the dosage minus the demand equals our residual. And the example is just if you add 3.6 milligrams per liter to the water, and the demand is 2.2 milligrams per liter. You usually don't know the demand. It's more of how much you're putting in and how much is left over, so you can kind of calculate how much your demand is. And if you develop a kind of like a daily record of that, you can kind of understand how much demand your wastewater usually has. But when you subtract the demand from the dosage, that you're going to equal your residual. And so this example that says dosage minus demand equals demand, that's incorrect. It should say dosage minus demand equals residual. So the residual is typically composed of free chlorine and your combined chlorine. So free chlorine is your unreacted chlorine that reacts with water to form hypochlorous and hypochloric acid. And then your combined chlorine is that in the presence of ammonia, hypochlorous acid forms chloramines. And these chloramines are kind of the goal of disinfection with chlorine. You want to make sure that those are present. And I'll talk about that in the next slide. So hypochlorous versus hypochloramines is important because it's important to understand that hypochlorous is a very strong disinfectant. However, it degrades easily. So that means it's not going to be present in the wastewater after it reacts with stuff or after it's just sitting there for a while, because it's so reactive that it's going to be reacting no matter what, whether there's contaminants in the water or there's sunlight present or there's oxygen. The hypochlorous is going to get in there, it's going to react very quickly, very strongly, but then it's going to be gone. Chloramines, however, are weaker disinfectants, but they don't degrade as fast and they stay in the system longer. So they kind of act as a longer lasting disinfectant that can stay in the system. And they do need a longer contact time. So this may create the requirement for a detention time. Real quick, I meant to mention this at the beginning of the presentation, but you might notice that there's not a whole lot of pictures in here. We have been kind of working on making sure that we're using open source pictures. And I was not able to get a whole lot before this. So, future presentations, I hope to have a lot more, but I just want to mention that if it's not as lively looking as I would like it to be. Back to the presentation. So chloramines are created when ammonia is present and reacts with hypochlorous acid. So sometimes this is either ammonia that's already in the wastewater or it's added after you've already done nitrification in your biological process. And chloramines are often created intentionally due to their enduring properties. Like I said, this is kind of the residual that you want to see to make sure that you're meeting your permit requirements. For example, I worked at the Albuquerque Wastewater Treatment Plant. We call that the Southwest Reclamation Plant. And at the Southwest Reclamation Plant, it is dosed with hypochlorous. It is the liquid hypochlorous. And it's also dosed with ammonium sulfate to create those chloramines. So they create the liquid chlorine, and they add that, and they dose it with ammonium sulfate to create that long-lasting disinfectant. And also, so that increases the contact time available for that disinfectant as it stays in the water. So a little about the structural and the chemistry of chloramines. So chloramines can exist in the form of mono, di, and trichloramines. And the pH of the water, the wastewater that they're in, usually determines those concentrations of each of those different forms. So below a pH of 4, you're typically going to have trichloramines, and they're going to be existing by themselves. At a pH of 5.5 down to 4, you're going to have dichloramine, and that's going to be the only one present from there. And then monochloramines and dichloramines both exist at the pH level of 6.5 and 7.5, which is our typical wastewater levels. Usually you're going to see it around 7. Sometimes a lot of plants run a little below 7 due to the alkalinity that's consumed during nitrification. Anything above this, above like 7.5, you're typically going to only see monochloramines. So if your water is real caustic or basic, they're going to exist in the form of monochloramines. You might see test questions like this, where the question is, if from a pH between this and this, what's going to be the dominant form of your chloramine? So that's something to keep in mind if you're studying for certification. So something important to understand about that interaction between chloramines, dosage, and demand is breakpoint chlorination. This is just going to be a quick graph about it. Breakpoint chlorination could be its own presentation, and I do believe we either in the future develop a webinar that we're going to put out, or just like an educational video that you guys can refer to. But this kind of shows that as you're dosing the wastewater, there's a point where your dosage that you're measuring with your residual is just going to show steadily increasing. So this is when you're destroying chlorine residual and the compounds that it's working with. You can see that between 0 and 1, where there is no residual. It's because all that chlorine is reacting. Between 1 and 5, and that's not always credited, but this is just an example. It shows that you're forming those chloroorganics and the chloramine compounds. So that's where you're creating your combined residual. And then as you're creating that, you'll get to a certain point where that residual will decrease because those chloramines are now starting to react with the contaminants in the wastewater. And now they're being destroyed, and your chlorine residual is going down again. And then you're going to add a little more of your free residual or your free dosage, and then you're going to get to a point called the breakpoint chlorination, and that's when you destroyed all the contaminants that are going to react with your free chlorine. All the contaminants are going to react with your chloramines and chloroorganic compounds, and then you're just going to start increasing again, and you'll have your combined residual and your free residual. And that's that's going to be a combination of free chlorine and your chloramines and chloroorganic compounds. And so sometimes you're going to, for the test, you might be asked to kind of identify some of these points. Like where are chloramines being created? Where is breakpoint? Stuff like that. So that's why it's important to understand this kind of graph. So testing for the chlorine residuals. Most common is a field test where it's called a DPD test, and it must be done within 15 minutes of sampling. It's very simple. So you typically take your wastewater sample, you add a reagent to it. In my experience, it's usually pink. You're going to shake it for a minute, and then you compare it with either a color wheel or you insert it into a spectrometer, which shines light through it and measures out the amount of, because the reagent reacts with the chlorine and it's going to turn a certain color. So the darker that color is, the less light that can pass through. So the spectrometer is going to report a higher reading based on how dark that sample is. So now we're going to talk about the different types and their processes. So the first is gas chlorination. Chlorine gas is typically a greenish, yellowish gas. It's 2 times heavier than air. So that means that it's going to, if it escapes anywhere or it's in a room, it's going to sit at the bottom and it's going to stay there. It's not as likely to float away because it's heavier than air. It is typically compressed into a liquid form when it's in those cylinders. Those come in between 150, or there's two types that are typically used, 150-pound and 2,000-pound cylinders, which are going to be attached to a chlorinator for dosing. And then the gas chlorinator consists of a pressure regulating valve, a feed indicator, and a flow regulating device. That's typically called a needle valve or a B-notch plug. For the test, it's important to understand these components and possibly also be able to identify them on a diagram. And then there's also an injector or ejector, which is what's used to put the gas into the water. Real quick, I'm getting a warning message on my GoToWebinar. Avery, Kristen, can you guys still hear me?
Yeah, I can still hear you.
Okay, awesome. Just wanted to double check. The chlorine pressure regulating valve, that maintains a constant negative pressure inside the chlorinator. So it keeps it liquefied, and then as it's distributed, that's when it becomes a gas. And then the feed rate is controlled by the needle valve or V-notch plug and reads in pounds per day. And it's important to understand the amount of flow that can be distributed for chlorine gas. And we'll talk about that in this slide right here. So there's maximum feed rates, and the maximum feed rate for a 150-pound cylinder is 40 pounds a day, and the maximum feed rate for a 2,000-pound or 1 ton tank is 400 pounds per day. And what happens if these rates are exceeded, the tank will begin to frost over and can rupture, causing, allowing all that gas to escape, and then you have to worry about all those hazards that we talked about. So an important safety for when you're working on chlorine gas is that gas masks should be available to allow operators to escape when a leak occurs. There should be self-contained breathing apparatus or SCBAs available when the work is being done in a gas chlorine atmosphere. And it should hold at least 30 minutes of air, And there should also be alarms in place that show when the pressure in the air tank has 5 minutes remaining. Every chlorine cylinder should be equipped with a fusible plug. This melts at 157 degrees to prevent the cylinders from rupturing at this temperature. The idea is that if this tank is being held and it's very hot in the area, that instead of rupturing and exploding and that gas going everywhere and being an environmental hazard, that'll start to leak. Now, this is also not desirable. However, that slow leak where the chlorine can react slowly instead of just all escape at once, and it can hopefully set off an alarm where it can be addressed, is preferable to an explosion. There's also chlorine evaporators, or hot water heaters surrounding the tanks that acts as a means to evenly distribute heat throughout the cylinder. And these can also be tubes with warm water that surround the chlorine line. And this is to make sure that the freezing doesn't occur. That can cause rupturing. So now we're going to talk about chlorine powder. In its dry form, it is known as HTA, or calcium hypochlorite. The powder is 65 to 70% chlorine, and it's 2 to 3 more times expensive than chlorine gas, but it is much, much safer to use because typically you can just scoop it in to your flow, or you can have some sort of meter that distributes it. And so the dosage is accomplished by diluting with water and pumping it into the flow. So you're just adding this liquefied powder. And typically with the HTH, care must be taken to avoid skin contact and inhalation. You can have some of those same effects as gas chlorine, but it's not as intense. It does need to be stored in a cool, dry place. You don't want water because then you get up with the hydrochloric acid. And then also contact with petroleum products or organic solvents can result in violent explosions. So make sure they're not stored in those kind of same maintenance areas. Next, we have hypochlorination systems. This is what's actually happened here is you create your own liquid bleach, and it can be pumped as bleach or diluted HTH. So bleach solutions typically have a 3 to 12% concentration, and a lot of times they can be produced on site. So again, at the plant that I worked at, we use water, salt, and electrical cells to produce sodium hypochlorite, or NaOCl. And this also, what happens is you're mixing water with salt, and it's going through this electric cell, and it's pulling, there's a reaction, and it creates that. So salt is just typically sodium chloride. So you're getting those oxygen molecules from your water, and you're also producing hydrogen gas, which has to be off gas for safety. So with chlorination, if you're introducing the water to a point source, you are required to have some dechlorination afterwards. And this is, of course, due to the reactive nature of chlorine, like we talked about, and it must be removed before it's discharged. And typically this can be accomplished by long detention times. Like we talked about, it's very reactive. Whatever's in the water is going to react with it no matter what. The oxygen above it, the air above it, anything like that. There's also aeration. So this is where you're forcing bubbles at the end of a long, narrow chlorine basin and allowing that oxygen to react with it through that contact time. It's also such thing as simply sunlight. So spreading chlorinated in a thin layer and exposing it to sunlight is a good way to do that. You might just have an outdoor tank. There's also activated carbon, which can absorb chlorine. And then also there's chemical reactions that can be used, such as sulfur dioxide, which reacts very readily with chlorine. And because of its weight, its chemical weight, it reacts at a 1-to-1 ratio with chlorine. So like I said, sulfur dioxide is widely used, and it's preferable because it's safe. So it's not reactive, it's not toxic, and it uses the exact same equipment as chlorination. Its density is similar, so that's like what we talked about with its molecular weight, and it's not flammable or explosive. However, it can be toxic in large quantities, and when we're combined with moisture, can form sulfuric acid in the right conditions. When it reacts with chlorine, the chlorine becomes inactive. So it's no longer reacting with anything because it reacts with the sulfur dioxide. And then also excessive sulfur dioxide can result in dissolved oxygen reduction, increased BOD, and a decrease in the pH. So typically you want this to follow your biological processes, and sometimes it may require some pH adjustment. Or you use it on water that already is high in pH. So next we're going to talk about a different type of disinfection. And this is going to be ultraviolet or UV systems. So ultraviolet light is used to damage the genetic material or DNA of microorganisms so they are unable to reproduce. If they are unable to reproduce, they can no longer increase in number and act as pathogens. So UV has gained popularity recently because it's safer than chlorine, and it's and recent advantages in technological efficiency. So the technology has gotten better and more easy to use and apply. So a little bit about UV systems. UV light is produced by low pressure mercury lamps, which are immersed in the flow exposing the microorganisms. These lamps are arranged in a rack configuration to allow all of the flow to be exposed. One thing to be aware of this is sometimes a screen is needed to kind of capture any plant material that might be in the system or growing in the system because microorganisms can't hide in the plant material. It's important to know the wavelength that is used for disinfection, and that's 254 nanometers. And this has been identified as the most efficient wavelength for disinfection. So this directly just attacks those microorganisms and their DNA. It's important for safety for UV systems to never look directly into the light bulbs and to take special precaution when handling the mercury lamps because mercury is also hazardous. It's also important to understand that the glass could be dangerous as well. So next we have ozone. Ozone is also very reactive, and some of the advantages of ozone is that it doesn't leave any harmful residue, and that's why people use it. However, direct exposure to ozone can cause health issues. But ozone is created by adding energy to atmospheric oxygen. So there's oxygen that exists in the atmosphere normally. You add energy to it and it reacts and forms O3. And ozone is a strong oxidant, which makes it an effective disinfection and virus killer. It must be generated on site though, due to its unstable nature. You can't transport it anywhere and you can't really get it in tubes. So some advantages of ozone are that it's more effective than chlorine in destroying bacteria and viruses. It has a very short contact time. Like we said, there's no residuals that can be hazardous. There's no shipping hazards because you produce ozone on site. And then also bacteria will not grow back unless it's shielded by molecules, such as like the plant material that we talked about. Some disadvantages is that its low doses may not be effective enough, and then the technology can be very complex and be dangerous. You're putting energy into oxygen, and then like also I said, like there's been incidences where like leaks were undetected and plant personnel were affected by it, and they didn't even like realize it until a bunch of people started developing breathing issues and stuff like that. And so that's going to wrap up our disinfection side of this webinar. So we have some poll questions, and if we can.
All right, here we have our first poll. Disinfection is designed to treat which of the following? And you'll select from BOD, pathogens and other microbes, core screenings, or ammonia. And go ahead and get those answers in. We'll be closing the poll in 3, 2, 1. And here are the results.
Let me see. One second. Let me pull that up. Why can't I see that?
And the results, we had a 97% chose the pathogens and other microbes.
Okay, awesome. So that's the correct answer. I'm glad most of us got it. Just a quick breakdown of the other answers. BOD and ammonia are typically treated in our biological processes, and core screenings are treated in our pre-treatment. Whereas, like we talked about, pathogens and other microscopes are in disinfection. So we want to remove those.
All right, and I'm going to launch that second poll. Which of the following is used to remove chlorine? And you can choose from sulfur dioxide, sunlight, aeration, or all of the above. And get those answers in. We'll be closing this poll in 3, 2, 1. We had a majority chose all of the above.
Awesome. So, as we talked about, chlorine is very reactive, and so exposure to any of sulfur dioxide, sunlight, or oxygen will result in dechlorination.
Third poll. Which of the following is not a form of disinfection? Clarification, chlorination, ozone, or UV radiation? And get those answers in. We'll be closing this poll in 3, 2, 1. And we had a 97% chose clarification.
Awesome. Good job, everyone. So again, chlorination, ozone, and UV are the 3 that we just covered for disinfection, and then clarification is usually used to separate solids from the wastewater.
All right, we're taking this back to you, AJ.
Okay. Can you guys see my screen?
Yes, we can still see your screen.
Okay, thank you. All right, so next on to sludge handling. So for when you have your sludge is going to be your different solids you get throughout the process, whether that's primary clarification, secondary clarification, your different waste activated sludge lines and stuff like that. So the solids or sludge must be stabilized and reduced in volume before it can be reused or disposed of safely and economically. The solids handling process stabilizes the sludge and reduces its volume. And there are 4 common processes for dewatering. This is thickening, or I'm sorry, these are 4 common processes that are involved in sludge handling. This is going to be thickening, digestion, dewatering, sludge disposal, and reuse. And then dewatering can take place before digestion to support the process or after to more easily transport solids. So first we have digestion. Digestion is where we stabilize the sludge by breaking it down into simpler components. What we do is you're converting solids to gases to reduce the overall sludge volume. And then, this is useful because methane can also be used, or the three gases that are typically produced are carbon dioxide, CO2, methane, CH4, and H2O, water. Methane can be used for power production, so it can be useful. Stabilization is done to prevent odors, human exposure to pathogens, and also attracting vectors. Vectors are animals that spread disease. And as we discussed in previous slides, oh, I'm sorry, no, this is the next thing. Primary sludge is unstable and secondary sludge has been partially stabilized. So that's important to, primary sludge spends the most time in digestion, and it's the most important one to digest. And secondary sludge, as we discussed in previous slides. Wait, hold on. I don't know why I wrote this. Sorry, I had a note for myself, and I don't know why I had it there. But so digestion can be anaerobic and aerobic, meaning with or without air. And then chemical stabilization is also possible, but it's not very common. It's typically accomplished with large amounts of lime to increase the pH and make the environment unlivable for pathogens. But like I said, this isn't a very common treatment process. So first we're going to talk about anaerobic digestion. This converts our sludge from a primary and secondary clarifiers into stabilized sludge that is relatively odor-free and more easily dewatered. So during anaerobic digestion, volatile content is reduced 30 to 60%. Our volatiles represent the organic components of wastewater solids. So anything that is alive or previously alive. And so what happens during digestion is fats, sugars, and proteins are converted to short-chain fatty acids, which are broken down further to gases. And this relies on two types of bacteria. We have our acid formers, or saprophytic bacteria, and our methane producers, which are our archaebacteria or archaeans. And those typically require an environment of a pH between 6.5 and 7.6. The balance must be maintained for your pH so the acid producers don't overwhelm the methane producers. If the pH gets too low, the digester can become stuck or even go sour. So sludge is pumped to dewatering process after digestion. So a little bit about the operation. Anaerobic digesters occur in 3 temperature ranges. This can be psychrophilic, which is between 10 and 20 degrees Celsius, or 50 and 68 degrees Fahrenheit. We also have mesophilic. This is kind of the temperature range that we see as ideal. As you can see, it's kind of near our body temperatures. And it's the most common range, and also produces a high level of methane and has shorter detention times of 25 to 30 days, which don't seem very low, but comparatively to the other two, it is. And those processes typically utilize primary and secondary digestion. There's also thermophilic, which is a very hot temperature loving bacteria. And this can be difficult to maintain because of those high temperatures and the sensitivity of those organisms if you go below those temperatures. It's not common to be used because it also produces poor liquid and solid separation. And temperatures are typically maintained with heat exchangers. Heat exchangers use hot water to transfer heat to the sludge, or heat exchangers, and can be located inside the digest. Those can be located inside or outside. Water can be heated by digester gas, propane, or even natural gas. Sometimes this water is a cool down product of another process, such as energy generators. So a little bit about anaerobic digestion. Our detention time is 25 to 30 days. This is going to be our mesophilic digestion that we talked about. The feed should be slow and steady. Typically, there's a rotation that's established. You know, you have a couple digesters, you do them each for a certain amount of time throughout the day. The sludge temp should be monitored and the heat exchange should flow adjusted as needed. So for mesophilic, like we said, that it's 95 degrees Fahrenheit. And we want to make sure the temperature change does not exceed 1 degree Fahrenheit per day. It can either throw off the bacteria, or if you heat it too quickly, you can also turn that into dry cake, and it'll mess up your operation as well. And then also mixing should be constant in your digesters. And this can be provided by mechanical mixers, or circulation of the sludge, or both. So there's also aerobic digestion. This is kind of considered an extension of secondary biological treatment. You're usually adding oxygen, and it's applied to small to medium plants that use extended aeration, activated sludge, and SBRs. So solids are held in a tank and provided air and mixing, but no additional heating. You're trying to kind of have it more do those aerobic properties. And this is because you're not adding a food source. This is what's called endogenous respiration. And microorganisms actually use each other as food. And this results in the release of CO2 and water, which is called aerobic respiration. And volatile solids is reduced 20 to 40%, and the detention times are between 20 and 30 days for operation. So it's also important to know that this is not always considered an effective, as effective as anaerobic digestion. So operation of aerobic digestion, so it can be similar to your biological processes where you're using surface aerators, a fixed bridge aerator, or blowers, and you want to maintain a DO concentration of 1 milligram per liter, and it should never go below 0.5 milligrams per liter. There's also supernatant tubes, and supernatant is the decanted liquid that's removed and returned to the headworks. This water can contain filamentous bacteria, and also your aeration must be turned off to allow for that separation. Those bacteria you want to move to the headworks so they can keep being processed, as they're a source of bulking issues in the biological processes. These digesters should be taken offline and cleaned at least every 3 years to remove sediment buildup and to inspect the equipment inside the digester. If the solids are not removed, reduction of solids, the solid reduction or the process that you're trying to create can be decreased. It's good to have this pH over, or it's required to have the pH over 7, but it's not usually an issue because these typically follow alkaline processes like nitrification that increase the pH. What you'll typically see for them is the total solids of the product will be 1.5 and 4%. So after digestion, typically we have sludge thickening. So sludge, after digestion, it still has it's considered sludge, but has a high water content, and it's difficult to transport or store. Even the thick sludge that comes out of digestion is 5 to 6% solids and still 90% water. Sludge thickening can be utilized before or after digestion. A lot of times you have your waste activated sludge and your digested sludge that need to be thickened. And then also thickening methods focus on separating the solids from the water. That's called the dewatering process. And the water is returned to the treatment process. Dewatered solids can be digested, disposed of, or used for land application. And a lot of times we have polymer utilized to enhance the thickening. We're going to address a couple different types of those sludge thickening processes now. So we have gravity thickeners, diffused air flotation units, or DAF units. There's also belt presses, centrifuges, and sludge drying beds. So gravity thickeners are a similar concept to clarifiers. You're using gravity to separate the water from the solids. The solids are pumped out, and it's similar to sludge, and the liquid water can be decanted. The ideal sludge is based on detention time and sludge age. Older sludge does not always work well because they are subject to denitrification and gases from septic conditions. This is going to be the same as we see in clarifiers, where primary sludge is best used because the secondary sludge has a low solids content and does not settle as easily. So the solids concentration from these, your product is usually going to be 2 to 4% or 6% if polymer is used. There must be a balance kept with the depth of the blanket, so it's thick enough to achieve compaction, but must be removed before that nitrification can occur. Next, we have DAF units. So this is typically secondary sludge mixed with polymer and air to separate solids that flow to the top of the basin. You might see this used for activated sludge that's being wasted out of like a secondary clarifier after it's been used in a biological process. There's typically a scraper that scrapes solids into a hopper. So this is typically a big tank. There's a mixer, which is mixing oxygen, polymer, and your sludge. And the water is separated by allowing that solids to flow to the top, and the scraper scrapes the solids into that bin, like I said, and then the water is moved to the other end. So what happens is air goes from a high to low pressure in these systems, and small bubbles will form, inducing that flotation. And secondary sludge is preferable to primary sludge because the organics have already been partially broken down. And primary sediment tends to deposit primary sludge tends to deposit sediments. And then you also want kind of like a younger secondary sludge as opposed to a older one. So something about DAF operations. Typically you want to maintain a depth of blanket of about 6 to 8 inches, and that's the blanket floating on top. That is controlled by adjusting the speed of the scrapers. So increasing the speed decreases the thickness of the blankness, and vice versa, where decreasing the speed increases it. So thickened sludge will typically have a 2 to 4% thickness or solids concentration without polymer, and a 3 to 5% solids concentration with polymer. This can be measured by drying and evaporating at 105 degrees, which is typically done by labs. And then also something to keep in mind is the air pressure determines the amount of air available for flotation. Typically you want 0.1 or 0.01 to 0.1% air to the solids, and increasing the recycle rate of your DAF tank will increase the amount of air to the DAF inlet, which is sometimes called a mixing box. Each system is going to be unique though, and the required air is going to be depend on the design of the system and your wastewater characteristics. However, effluent should have a TSS concentration of about less than 100 milligrams per liter. So next we have belt presses. So these are typically two endless belts that are on rollers and that are pressed together. They're over a series of rollers that resemble like a steel frame. So what happens is polymer is ejected into the sludge and dewatered into a drainage basin before entering between the belts, so that polymer mixed sludge is fed into the belts, and it's pressed between them, and the belts have perforated and non-perforated rollers where water is forced out of the sludge. The liquid effluent is returned to the treatment plant, and the sludge cake is scraped off the belt and carried off the conveyor. So this is basically just putting sludge between it and squeezing the water out in between these two belts. And the belts are typically washed off at the end to prevent plugging. So some information about belt presses. Typically primary and digested sludge are better suited for the belt filter presses. They require smaller amounts of polymer, and some of the solids concentration that you will see is from primary and primary digested sludges between 25 and 35%, or up to 30% for the digested. And secondary sludges tends to have lower total solids, so it's not as efficient, of between 17 and 20% of the product. So it's important to condition sludge for belt presses. We want to make sure that the sludge feed is consistent and that polymer is added. The belt pressure, the belt tension determines how thick those solids are going to be and how much water is going to be squeezed out of it. So if you have more pressure, you're going to have higher solids concentration. And then the speed depends on the flow rate and the concentration of the influent sludge. So the speed must be fast enough so washout doesn't occur, so you're not just dropping it on there, and because it's not moving, all the liquid is just flowing over the sides, but it also should be slow enough to maintain a good effluent quality. If the belts are moving too fast, you're going to get a lot of solids in your water that's supposed to be dewatered. Typically, these belts are made of nylon or polypropylene, and they have a high porosity and so the higher porosity results in poorer effluent quality because there's not water isn't allowed to go through. However, if you have low porosity, that can result in binding and plugging, and no water can pass through. So another form of dewatering is our centrifuges. Feed sludge is fed into a rotating bowl that kind of works on a centrifugal property. There is an outside bowl and an internal scroll where they spin really fast and in opposite directions. The solids go to the bowl, and that internal scroll will move those solids to one end where they can be released, and then the liquid centrate discharges to the opposite side of the centrifuge. So it's important to use secondary sludge in this process, typically after digestion, and this is to mitigate sediment deposition, which damages the equipment, and also off-gassing from those unstabilized sludges. So in order to increase thickness, you want to increase your bowl speed, but this can also result in a worse effluent because it's moving faster and doesn't have that time for the polymer and the the sludge molecules to bind to each other. So the differential scroll speed can also affect cake thickness and centrate quality. As cake concentration increase, is solids removal efficiencies decrease. And again, that's due to kind of the speed not allowing it to work its operation. It's also important to understand the liquid depth. The liquid level in centrifuges can be changed by adjusting where the effluent weirs are. So that's going to be inside your centrifuge. And then also polymer is added to improve cake thickness and solid recovery and allow them to stick together more efficiently. Typically in a centrifuge, the feed going into it is 4% solids. This thickened sludge is 5 to 30% solids, and your solid recovery rate is about 90 to 99%. So you can see it's very efficient. So we're going to talk a little bit about polymer. Like we said, they're used for centrifuges, DAPs, belt pressures, and also rotary drum thickeners, which is another type of dewatering that we did not cover, but some plants are using. So polymers are large repeating molecules that dissociate to positively charged cations and negatively charged anions in water. Positively charged cations are used in dewatering processes. And this is because the sludge and biosolids are typically negative. So those positive charges connect with the negative charges. Typically, these are proprietary materials, and they're developed by companies, and they kind of keep their secrets, what they're made of. But they can come in liquid and powdered form, and they also require bench testing to determine how useful they are for your specific dewatering plant. And they're the forms get vary based on what type of technology is being used. So next we have sludge drying beds. These are typically utilized by small to medium-sized plants with less than 5 mgd. One thing to know about them is that they are land intensive and require warm climates. There are typically 3 types. There's sand, asphalt, or concrete, and vacuum filter beds. So typically a layer of sludge is placed over these materials. They're allowed to dry. They have a draining system where it collects some of the separated water. It'll convey that to the front of the plant. And then that, as the sludge dries, it needs to be scraped off and disposed of. So we have a sludge reuse and disposal. Typically, this process is regulated by Title 40 of the Code of Regulations, Part 503, which covers solids disposal. This can be composting and land application, which results in a high level of nutrients for the compost. This is regulated for contaminants, including pathogens and heavy metals. And also, depending on the permit or what it's being used for, may require thermal composting. There's also surface disposal, where sludge is directly injected into the surface and mixed with the soil. But because it could still have pathogens and stuff in it, there is a groundwater permit required, and sampling needs to be done to make sure it's not going to damage the area. And then finally, it can also just be landfilled. This is not environmentally friendly, and it's not desirable because it is land intensive and requires a special hauling permit, and usually is only done for economic viability and due to poor sludge quality. And that is the end of our solids handling. Went a little fast, so my apologies if we didn't catch a whole lot of stuff. We were trying to pack a lot of info in, but we do have 2 more poll questions for you guys.
All right, I am launching that 4th poll. Sludge digestion is designed to do what? Break down debris removed from wastewater influent, stabilize and reduce volume of solids, disinfect wastewater effluent, or dewater solids. All right, get those answers in. I'll be closing this poll in 3, 2, 1. And we had a 77% voted for stabilize and reduce volume of solids.
Okay, awesome, good. So looks like most of us got it. If you guys remember, that disinfection is how we disinfect wastewater. So none of you guys, it doesn't look like many people chose that, so that's good. The dewatering part is done by the sludge thickening processes. And then typically the first one, breaks down debris and removes it from wastewater. That's typically going to be our pre-treatment processes. So digestion, like we said, we want to stabilize and reduce the volume by breaking down the microorganisms in there into smaller components, releasing some stuff as gas, so it's easier to handle.
Right. And here is that last poll. Anaerobic digestion occurs in the absence of what? Water, anaerobes, oxygen, or pathogens? All right, and we're going to go ahead and close that poll in 3, 2, 1. And 97% chose oxygen on that one.
Awesome. So it looks like everyone kind of remembered the difference between anaerobic and aerobic. So aerobic is when we do have oxygen. To perform anaerobic digestion, we need our anaerobes. Water can be present or not present. And then pathogens can be anaerobic digesters. So good job, everyone, on that. And
AJ,
now,
if you,
oh, go ahead.
I was going to say, if you've got time, we did get a couple of questions. If you've got time to answer them.
Yeah, of course.
The first one is stepped cascade aeration considered a viable option for dechlorination?
Stepped cascade aeration. Honestly, I've never heard of stepped cascade aeration. I'm not really positive what exactly that is. I could research that a little further if you'd like, and I can connect through Avery and Kristen to kind of address that later. My experience with it is I've usually seen like bubblers, so like someone just kind of, almost similar to like membranes that distribute dissolved oxygen in biological process.
Okie doke. Our next question is, when using DPD tests for chlorine in effluent, is using a color wheel acceptable for reporting?
I believe that for reporting, it does have to be analytical, and it does have to follow the standards methods. And I don't believe the color wheel is precise enough. I would refer to your permit and the standard methods to determine for sure. But I don't think the color wheel, because it does leave room for it is subjective, and I don't believe it is accurate enough. From my understanding, I think it does have to follow the standard methods. I don't think the color wheel's on there.
Okay, got two more. One is, at what methane content is gas flammable enough for heat exchange?
That would be something else that we'd have to check as well. Yeah, I'm not positive on that. We can research that though.
Yeah, and that I guess might be dependent on the design of your system as well. And then last but not least,
it's going to depend on what you're using for, a heating device as well, what type of cogeneration. But yeah, it might be a manufacturer design characteristic, but I am not completely positive. That's a good question.
Okay. And our last one is another sort of pretty technical one. How long should air be turned off before decanting an aerobic digester? I presume this is for testing.
Well, it's in order to decant that water that's going to be left in there.
Okay.
Again, we can look into that and let you know. That it might also depend on the manufacturer of that aerobic digester. Yeah, some of these questions are probably, plant specific, but we can definitely help assist in kind of figuring out that information. When you get those questions, does it show you who asked them so we can?
Yes, it identifies who they are, so we can definitely follow up afterwards.
Yeah, so we could do a little bit of research and follow up on those, probably either later this week or the beginning of next week.
Okie doke. Well, that's the last of the questions that have come in. I'll turn it back to you.
Awesome.
All right. Thank you, AJ, for sharing your expertise with us today. Following this webinar, everyone, you will receive a follow-up email with the slides from today and a link to the recording. Thank you again. We hope to see you at future EFCN events.
Thanks, everyone. Thanks for your questions and thanks for your time. We'll try to follow up with those as soon as possible.